Hi, welcome to Analysis and Design of a Flyback. This is part 9 and the topic will be input filter design. Okay, the input filter is a very important part of a switching power supply. It's often overlooked, but there's very good reasons why they should not be overlooked. Okay. First of all, why do we need a input filter? Okay, why not just connect it to the voltage source? Okay, well, the main reason would be that you have a switching supply, and switching supplies generally produce peak currents, and depending, you can have quite a bit of currents, and typically some of the power supplies can start anywhere from 100 kilohertz and they can go up to the megahertz. Okay, and those produce currents that if you don't filter them out, they can actually pollute your input voltage, your bus. So basically, you just want to be sure that the currents are managed. Okay, now what makes a good input filter? Okay, well, the object would be it needs to attenuate the noise. And when I'm talking about noise, you want to be sure that you attenuate the differential mode noise, diff mode. Okay, and diff mode is from your positive and negative rail, and then you also have common mode. And that's typically from plus and minus rail to your chassis. Okay, now I won't go too much into this on this video. I'm going to concentrate on the differential mode in this video. Okay, and at least how to simulate diff mode. Okay, another property, very important, must have a lower output impedance. And when I say lower output impedance, I'm referring to the input filter. In other words, the output impedance of the input filter has to be lower than the input impedance of the converter. And typically this is known as the middle criteria. Okay, it's very important. If you don't observe this, you will end up having oscillations. So basically, you can say the Z out of the input filter in has to be lower than the Z out of the converter. Okay, if you don't satisfy this, you're going to have oscillation. Okay, and hopefully we'll do a simulation demonstrating that. Okay, another, which is kind of related to the Middlebrook, is must be properly damped. So if you don't have your input filter properly damped, you're going to have a ringing whenever you have a disturbance. Okay, so how to design an input filter? What are the things that you need to know? Well, one of the first things that I would need to know is I need to determine the fundamental frequencies. In other words, what are the harmonics? Okay, you got to remember that if you were to draw out a flyback, looks something like this. Cap and your load, and then this is your VN. Okay, so when the switch closes, you're going to have a current that goes like this, and then when the switch closes, it goes that. Okay, so this is a current that would be coming in, and what you need to do is you want to know what are the frequency harmonics of that pulse. Okay. Second, okay, well, you need to know what are the EMI standards that you will be testing. Okay, there's several standards. The one that I am more familiar with, and I'll be using it as an example simply because I'm just a little bit more familiar with it, and because I do military power supplies, is the Milspec 461. That's the one that I'm going to be using. Okay, but the procedure should be the same as with any of the other standards that you may use. Okay. Okay. So if you look at Milspec 461, this is the plot that I would use. Okay. This is the plot that I would seek out, and this is the information that or the plots that would extract the information. Okay, basically this is the differential mode conducted emissions plot. Okay, basically this is for 30 to 15 kilohertz. Okay, 30 being right here to 15. Okay, so 15 would be here, and 30 approximately right there. Okay, and what it's telling you is that between those frequency, or actually that frequency here, it looks like 2K. Well, let's see if I can. 2K. You're allowed 130 watt. If you notice, it's dB microamps. Okay, so this point is 130 dB microamps, and then if you notice, it has a downward slope and so forth. Okay, then the second plot is this plot, which is kind of a continuation of this. Okay, and this is from 15 kilohertz to 100 megahertz. Okay, now this is the plot that I'm going to be using. Okay, and the reason I'm going to be using this is because I'll be using the example from the previous 8 videos. I'm using the little flyback example, and on that one the switching frequency is 100 kilohertz. Okay, so basically I want to be sure that the harmonics of my switching power supply, which is 100 kilohertz, are below this minimum. Okay, so if I look in here on the y-axis, I go to 100 kilohertz, and if I go up, okay, I hit the plot, and that tells me that I should be at around 60 dB microamps. Okay, so that is my limit. Okay, so like I said, switching frequency is 100 kilohertz. Therefore, my current conducted emissions at 100 kilohertz is around 60 dB microamps. Okay, so the question would be, well, what is 60 dB microamp? What is it? What's the absolute value? Okay, so let's calculate that. Okay, well, when you use dB microamp, it means that the reference current is 1 microamp. Okay, So basically dB microamps equals 20 dB microamps times log times the current that you'd be testing. In this case, it's the current of the conducted emissions, and this would be the reference 1 microamp. So this is the absolute that you're interested. Okay, so if we solve for ICE, basically bring this underneath, you get that, and then if you solve for ICE, you end up with this equation. So this is the equation that you want to use. So this will tell you the absolute current, or actually the minimum absolute current that you're allowed into the bus. Okay, so in this case it would be 1 microamp times 10 to the 60 divided by 20 power, and I come out with 1 milliamp. So this is the maximum current allowed into the bus. Okay, so now we have our first parameter. We know this is our limit. Okay, so what do we do next? Okay, well, we need to calculate the primary current of the converter. Okay, and in our design that I showed in the previous 8 videos, I have used a Flyback converter. Okay, and these are some of the design parameters that I use to design that switching power supply, or that Flyback. And the design parameters was to have 24 volts input, a V out of 12 volts, current of half an amp, and once I designed it using a switching frequency of 100 kilohertz, I ended up with a input current average of 250 milliamps and a peak current of 1 amp, or at least approximately 1 amp. So I ended up with a waveform very similar to that. Okay, basically the peak current was close to 1 amp, and the average is 250 milliamps. So that would be the average, and of course it's going to have a T on of 5 microseconds and a period of 10 microseconds. Okay, so when I did the simulation, and let me go ahead and just show a quick simulation of that. Okay, I found the file. Okay, this is the simplified schematic. Okay, I'm not using a MOSFET, I'm using a switch. Okay, and when I run the simulation, excuse me. Okay, this is the plot that I get. Okay, and if I put the cursor up here, I get approximately close to 1 amp. It's actually 978 milliamps, which is close enough. So that would be that plot. Okay, so this is 970, I believe. Okay, so now what you want to do is you want to get a you want to convert or get the FTT of that waveform. Okay, and you can do that by doing a FTT of that particular. Let me go ahead and press delete that or comment out. So now it says that I'm going to do a FTT on IV3. IV3 is the current through the input. Okay, so here's the harmonics. So the harmonic is 300 it has an amplitude of 370 milliamps peak. Okay, so that would be that plot. Okay, so this transient waveform is decomposed into its harmonics. So this is what we're looking for. Okay, we know that the peak current at 100 kilohertz is 370 milliamps peak. Okay, and we use SPICE to do the FTT. Okay, so now we know that peak current, or the fundamental, at 100 kilohertz is 370 milliamps. Okay, so now we can calculate the attenuation needed from the input filter. Okay, so basically we need the input filter to basically attenuate the 370 milliamps. Okay, and we need it to attenuate or reduce it to 1 milliamp. Okay, so to do that, we need to express the attenuation in dBs. Okay, so how do we do that? Well, what you do is you plug it into this equation, which is the 20 dB log, and you put the desired attenuation. In other words, this is what you're going to go to. So you want 1 milliamp. Okay, and then this is the fundamental peak current. So to get the proper attenuation, you need a attenuation of negative 51.36 decibels. Okay. So now, for in designing the input filter, typically you would use an inductor and a capacitor as the input filter, and this basically describes the transfer function of a second order system. Okay, and basically it's 40 dB log, the resonant frequency that you're going to be operating at, or the resonant frequency of the input filter, okay, and this would be FSW. That would be the switch frequency, which is supposed to be 100 kilohertz. Okay, so what you want to do is you want to solve for FO. Okay, since we've already calculated what the attenuation is, negative 51.36, that is plugged in there. Okay, and we can plug in the 100 kilohertz right there if you wish, but we want to do is solve for FO, and after some algebraic manipulation, you end up with this equation. Okay, so plug in the numbers, and I get a resonant frequency of 5,199 hertz. Okay, now that we have the resonant frequency, we use this equation, and in this case I choose to solve for L. I end up with L here. Okay, and when I plug the equation or the numbers, I get 9.38 microhenries. Okay, so this would be a 9.38 microhenries, and the capacitor, I chose it to be 100 microfarad. So depending what you select as your capacitor, well, you'll get an inductor at that that will correspond to the resonant frequency. Okay, so let me go ahead and run a simulation then. Okay. Okay, here we have the input filter. Have inductor of 9.36 micro henries and the capacitor of 100 micro. And what I'm going to do is I'm going to go ahead and plot the AC response, and that is done by setting the input voltage, which is V1, to you enable the AC spec, and you put a magnitude of 1. Okay, and the output would be this node, and to plot you put the pound auto plot AC. 1 means it's the first plot, and it's a VDB parenthesis out. Okay, so we'll go ahead and plot that. See how it looks, and this is the frequency response that we get. Okay, so we can go ahead and use the cursors, and we can go ahead and put the cursors at 1 kilohertz approximately, and that is 100 kilohertz. And if you look at y2 minus y1, it's negative 51.39, which is the attenuation that we were hoping that we would get. Okay, so this means that it's working the way we intended it. Okay, now a little problem that I do see is this here, and that is the resonant frequency. Go ahead and put the cursor there, and that cursor is at 5.24 kilohertz. Let's see if that's close to the frequency. Okay, this is 5.299, so it's kind of close, not exact, but it's close enough. But if you note, what's more concerning, it's not so much that it's a little off. Is the concern is that it's got peaking. Okay, so this means that the circuit doesn't have any resistive components, and if you look, you don't have any resistive components. Okay, and another characteristic is at that frequency, the impedance looking in this direction is infinity. Basically, at resonance, the capacitant reactance cancels the inductor reactance. So basically, at that frequency, resonance, you have an open. Basically, they cancel out. Okay, and that's a problem because it violates the Middlebrook criteria, meaning that you want a very low impedance looking and into the filter. Okay, so how do we take care of that? Well, typically what you do is you damp the circuit. Okay, and a common way of damping the circuit is to use a capacitor with a resistor, a damping resistor, and typically to get very good damping, you make this capacitor 10 times bigger than C2. So in this case, we'll put 1,000 microfarad. Okay. And we put a resistor in series with it. Okay. Now, how do you calculate the value of the resistance? Would be the next question. Okay. Well, to do that, see if we can calculate that. And actually, it's fairly easy. What you want to do is the resistor damp is going to be equal to the characteristic impedance of the circuit, which is L and C. So in this case, we'll get the square root of 9.8 divided by 100 microfarad, and let's see what we get. Let's see. So what we can do is parentheses 9.38 microfarads divided by 100. Okay, and we raise that to 0.5, and I get a resistance of 306 or 0.306. Okay, so let's go ahead and try that. Make that 0.306. Now, that value is probably low enough that any internal ESR in series with the 100 would probably satisfy it, but I'm just go ahead and demonstrating this for demonstration purposes, that how it damps. Okay. There. So you notice now it's properly damped. So at that particular frequency, then instead of having a open, you're actually going to read 0.306. You're actually reading the resistance of R1, would be the output impedance of the output filter. Okay, so I think that's a pretty good simulation. So now what we're going to do is we're going to see is how does it attenuate this current, or the current that the flyback converter would be producing. And what you can do is you can model, instead of using a flyback, the flyback can be modeled as a current source. And what you do is you try to duplicate basically your primary current. So in this case, I'm going to use an initial value of 0, a pulse value of 0.984, okay, and this will produce the little sawtooth. I'll put a rise time of 4.98 micro, and a fall time of 15 nanoseconds. Pulse width will make it very small, 1 nano, and with a period of 10 microseconds. Okay, so let's go ahead and do a transient. And what I want to do is I want to go ahead and plot this current just to show that this is very similar to the primary current that we're trying to simulate. Okay, so we'll do a transient, and we want to plot I1, which is this one. I'll go ahead and turn this one off for now. Okay, and run a transient. Okay, so we can zoom in. zoom in a little bit more. So these are the pulses. Okay, this is basically what we saw using that other simulation. This here, the only difference is you don't have the little peak, but basically you have the same waveform there. Okay, and if we were to do a FFT, we'll get the same peak that we were expecting. Peak of about 374. Okay, so that is the current that is being filtered. Okay, so now we want to look at the current at V1. V1 would represent the filtered current. In other words, it would be the current that would be from your bus. So let me go ahead and just label this. This would be the bus. Okay, and this current source is the flyback. That would be the model. So we're going to go ahead now. We're going to plot this current. Okay, and we expect the current to be close to 1 milliamp. Okay, and that would be that current. Run the simulation. Okay, so the top would be the current from the flyback, and the bottom would be the filtered. Okay, now gotta remember that this is the average current. We had said that we're going to have about 250 milliamps of average current, but this is the peak to peak. Okay, and if you do a FTT, okay, let me go ahead and rerun that. Do an FTT, which is these two. Taking the FTT of this current and the FTT of that current. Okay, so this should be filtered, it should be attenuated, and we expect about 1 milliamp, or at least close to it. Okay, here it is. And what I'll do is, let me move this. This would be, I'll paste it in the second one. Okay, here we go. So here, let's go to maximum. Okay, here's the maximum, and if you notice, it's 939 microamps. Okay, so that's the current going into the bus, and this is the original current that was being generated by the flyback. So in this case, we do see that the filter is working, and we have just the right attenuation, and seems to be working very, very well. And you can also see that some of the other harmonics up here on the unfiltered, you can see that they're even filtered even further. Okay, so this is the procedure that I use. This is a simulation technique that I use to set the input filter. I've shown the mathematics, how to do it. You can either put this on an Excel spreadsheet, or you can do, in this case I use MathCAD. You can enter your parameters, and then you can end up with with the inductor selection and the capacitor, and basically automate your input filter design. Hopefully this will design example will help you in designing input filters. Thank you for watching.